Okay, let's move on to histogram processing. This is section 3.3 of our book. Well, everybody knows what a histogram is, I hope. If not, please stop now and go back to your basic maths notebooks, internet, or whatever. Well, I'm assuming that you know what a histogram is here. So let Rk ranging over the number of intensities. Rk is the intensities of an L-level image that here we are denoted by f, x, and y. The normalized histogram of this image is defined by PRK. We're going to see later, this can be understood as the probability of pixel intensity, Rk, will be equal to the number of intensities, Rk, divided by the size of the image. Right? It's basically the number of pixels with this intensity normalized by the size of the image. And k is the number of pixels with intensity k. M and n is the number of image rows and columns, is basically the total number of pixels in the image. We define the sum of PRK for every k is always 1. Well, it's not defined. It's defined by this division here. So, and we are going to work with normalized histograms. In this sense, PRK is an estimate of the probability of intensity level occurring, of each intensity level occurring in an image. The reason behind studying histograms is that the shape of a histogram is related to the image appearance. You see that a darker image, let me get a pointer, a darker image has the histogram all concentrated here on the left half of the image, where left half of the values basically has only darker pixel intensity values, whereas a bright image has mostly high values of pixel intensities. An image of low contrast will have pixels intensities in the middle. You see there's no pixels in the darker areas, no pixels in the white areas. And what we want is a high contrast image, such as this, where we have all good distributions of pixels around all the intensity values. Why we want that? Well, we can see more details on this pixel, on this image, that we can then we can see here and there. Now, an image whose pixels occupy the entire range of intensity levels that are also uniformly distributed have high contrast. It's possible to develop a transformation function that can achieve this effect automatically. This is called histogram equalization. So the idea is to get an image like that, find a transformation based on the distribution of values that are going to transform each pixel here to a pixel here with a better distribution of pixel values, to an equalized histogram. That's a histogram that's more equalized than this one, than that, and this one. Okay. Well, as I said, it helps to see the details that we couldn't see before. So in a very general way, I have a probability distribution functions, PDF, probability distribution function. That is basically the original histogram, original image histogram. I'm going to apply, the idea of the method is to apply an equation on that that's going to transform this arbitrary distribution to a more equalized distribution of pixel intensities. This function has some constraints. It has to be monotonic increasing, meaning that if a value f in the original image is mapped into a value 10 in the output image, we don't want that a greater value than 7, such as 8, will go below the value of 7. This is what a monotonically increasing. We don't want to reverse pixel values. We don't want to reverse the order or the relative distinctions between pixels. And the mapping should be one-to-one. So we see that this is not a good transformation function because we have multiple values from the original image mapping to a single value. So that's one thing that we don't like. We want a transformation function more or less of this shape, similar to that. This is a monotonically increasing. So you see we're not inverting pixels values. One pixel that's greater than RK will always be mapped to an intensity value that's greater than SK. And there are no multiple values for the same input. A good transformation function for this is this very simple sum called cumulative distribution function. This is the cumulative distribution function, or CDF. Multiplied by L minus 1. So we see that this is a cumulative distribution function. This is a sum of probabilities. And we want to map each probability to an intensity value. So I multiply by the range. So this will be a kind of a percentage of the range of intensity values of an image. And the cumulative distribution function will count how many pixels have the value up to k. The idea is then to map each pixel in the input image with a certain intensity value, Rk, into a corresponding pixel with another level, Sk, in the output image. Right, so let's see how this works. For example, let's assume we have a 3-bit image with if it's a 3-bit image, it has 8 intensity values. If you don't understand that, go back to lecture 2. And let's assume that this image has size 64 by 64, so that the total number of pixels will be 4096. With the following intensity distributions. Zero intensity pixels with 0 intensity, totally black, gonna be there's gonna be 790 pixels that are totally black. If I divide this 790 by the total number of pixels in the image, this is the portion of pixels in the image that are totally black. This is .19. This is an estimation of the probability of seeing a totally black pixel, and the same thing to every other intensity values, and you see that we have 8 intensity values, each one with a certain number of pixels, of assuming this each intensity value. Now, the histogram equalization, let's see how this cumulative distribution function works. Let's apply the histogram equalization function, which is this. We're applying this function to this example. So we end up with, here we have what? So considering this distribution, then we want to apply the histogram equalization function, which I copied here just for the sake of, just for getting easier to understand. So L minus 1 will be, I have 8 values, minus 1 is 7, and this is the cumulative distribution, right? So let's pick up pixels with value 0 intensity and sum all of them. How many pixels are there of intensity 0? I'm talking not the number of pixels, I'm talking about this rate of pixels in the image with intensity 0. That would be 0.19, then 0.19 multiplied by 7 is 133. That's the first intensity value of the output image. Now for the second value, right, that's 7 times 0.19. For the second value, I'm going to sum the previous value, that's accumulative, right? I'm accumulating values of pixels, 1.33 plus 7 times the number of pixels with intensity 1. That's 0.25. Let's go back here. 0.25 multiplied by 7, summing 1.33, that's this value. And so on and so forth for every single value of found in this table. That's basically the definition of the image that we have, right? It's a 3-bit image, right? It has 8 values. These values have to be rounded to the nearest integer values into 0 and 7 because I still have only 8 values. It's still a 3-bit image, making the transformation functions from each value in the original function, in the original image, to a value in the histogram equalized image. The equalized histogram will be these values normalized by the number of pixels. Let's see how in the next slide this becomes clearer. Values are rounded to the nearest integer in the interval 0 to 7, making the transformation function from 0 to 1 to value 1 to 1 to 2 to value 3, as we found in the cumulative distribution functions. Now, the value in the S0, the transformation function S0 related to pixels values R0. Then in the output function, the values 0 are going to be mapped to 1, and the values 1 are going to be mapped to 3, and the values 2 are going to be mapped to 5. And again, where did I get these values? By applying this function. It's only that. That's this function, right? These are values of the equalized histogram. Then we normalize by the size of the image. We get then pixels with intensity 0 are going to be mapped to pixels with intensity 1. But there are 790 pixels in the histogram equalized image with this value, according to our initial statistics. So I get, and the same thing, I have to count them for the same thing for pixels with value 1 and pixels with value 2. And pixels with value 3 and 4, they are all mapped to 6, so I have to count then, you see that pixels with value 3 and 4 are mapped to 6. Then I have to sum all the pixels in the original image that had value 3, which are 656, plus 329. These are 985 pixels. Given these numbers, these final numbers of pixels, now the final count, I divide them by the total number of pixels in the image, yielding the equalized histogram. Graphically, I have the original histogram, something that's this one, is the original histogram. This is the cumulative distribution function. This is value 1.33, that's the first value here. This will be value 3, which is the second value, and so forth. And these are the normalized values of pixels in the output image, normalized by getting the number of pixels that fall into each of these bins, of these new bins, defined by S0, S1, S2, and so forth, divided by the size of the image, and I have the new histogram. We can see that this new histogram is a lot more equalized than the original histogram, where the original histogram has quite a lot of pixels concentrated on the dark side of the image, and not a lot on the bright side, whereas here is more or less equal, right? You will never get a straight line, totally no equalized histogram, because we can't create, or we can't introduce new information to the image. These numbers are calculated according to the number of pixels that I have in the original image, right? The idea is quite simple. I know that the explanation may be a bit seems to be a bit going to round and round, but the idea is very simple, and I strongly suggest you to read this section in the book to get a better grasp of histogram equalization. So this is an example of applying histogram equalization. In this example here, we see on the leftmost images, these are the original images. The original images, and these are the transformation functions. These are the application, these curves here are the applications of this equation to each one of these images. So this curve number 1 here is related to this image. This curve number 2 is related to the second image. Number 3, which is this one, is related to the third. And number 4, which almost the identity, is related to number 4, to the last image. Let's get rid of this. Now we can see that the transformation function applied to a very dark image is quite steep here. So what the histogram transformation function is doing is getting a narrow range of very dark pixels here and mapping to a wider range of pixels. So it's really, what it's doing is stretching the values of the pixels. Whereas I had a very narrow band, as the very dark pixels are going to be on a larger range, so creating a quite well-detailed image. And this is the histogram obtained in the end. This histogram is the histogram of this image here. Same thing for number 2. You see the number 2 is quite bright. So what it's doing is now getting a range of white in mapping. You see that the slope of this function is not as steep as this one. So it's getting, it's doing the opposite of this, right? So now it's getting a wide range of white in mapping to a more darker portion of the, I'd say a very bright pixels mapping to darker pixels here, creating a more detailed image. You see that these two are quite similar, and the histograms obtained in the end as well. Let's check the third example. The third example is a kind of blurred image, but it's a blurred on the median values of pixels, right? It's in the median, so it's not that dark, and it's not as white as this one, so it's in the middle values of intensities. So you see that the picture, the transformation function is pretty similar to the dark one, but it's dislocated to other pixel values, to the median pixel values here. Whereas if you pick up a very good image, quite good in terms of high contrast image here, you see that the transformation is the identity almost. reminding ourselves that the transformation is the cumulative distribution function written here. So you see that there was almost no change from the original image to the target image here, and the histogram is quite well equalized. All right. Let's move on. So we've seen histogram equalization. There is another technique called histogram matching or histogram specification. Whereas in equalization, we always try to produce a transformation function. And this is used for automatic image enhancement. But sometimes, if you just let the system to find the best histogram, the results are not as good. Sometimes you want to get a particular output. You know what you want as a final histogram for your function, for your image. And that's where histogram matching in the specification is. It's a kind of an extension of histogram equalization where you give to the system the histogram and you want the system to give you the mapping and to generate the transformation and apply in the image. So the idea is to find a mapping from an original image that takes it as close as possible to a previously identified histogram. Let's say we have here the original distribution on this side, and this is the target distribution. This is input. In this case, for histogram specification, I pre-specified as a user, I pre-specified the kind of histogram shape that I want to transform my image into. So the algorithm, it's very simple to explain the algorithm. But maybe when you read on the book, it may not be as clear because, well, I basically didn't like the way the algorithm is explained on the book. But there is an excellent numerical example, which I'm going to point you to in a moment. The idea is very simple. So we know how to get from the original image to an equalized histogram, right? We've just seen it, that histogram equalization. In the same way, we know how to get from this histogram to an equalized histogram. It's the same process that we used before, from getting the original image to an equalized histogram. It's the same one I applied to the pre-specified histogram to get to the equalized histogram, right? So if I know how to do that, then it's simply a matter of finding the inverse of this transformation function that takes the pre-specified histogram to the equalized histogram. I invert it, and now what I do is that if I know how to map this into this, and I have the inverted function, I just map this to this, and then every point here to that by using the inverse. That's the main idea, right? Well, this is an example on the book of the same thing that we've done for the histogram specification, for the histogram equalization. The book does for the histogram specification, where this histogram is specified by the user, and then the final the output image has this shape of histogram in the end. Right, let's see the effects of it. This is the original image of Phobos. I think that's one of the Jupiter moons. Saturn. Phobos is a moon in Saturn, if I'm not mistaken. So you see, no, you can't see, right? I can't see anything around this region, right? It's too dark. Too dark. And this is the original histogram for this region. You see the most values are all kind of clustered together into very dark pixels. Into very dark pixels. Now, if I apply histogram equalization with equalization, not specification, equalization, that's the first method, histogram method that we've seen today, we end up with this image. Why is that? Because if you get the original image, there is not a lot of information that I can play with. It's not only that, you see that this part of the image is pretty much homogeneous, right? So once you equalize that, all of these pixels are going to be mapped to the same region. So they're going to be equalized, but they're going to be equalized on the bright side. And we won't see much details as we want. Instead, if I give as input, this is my target histogram, this is my specified histogram. Who gives that? That's the user. That's you as computer scientists, as software engineers, as vision scientists, computer vision scientists, or image processors. You're gonna get this histogram pre-specified. This is the mapping function for this histogram to an equalized histogram. That's the function G. That's the function G that we've seen here, right? This is the function G. Now we invert it to get function G inverted. That's this function here. And now I apply the histogram transformation from the original image to the equalized histogram that's not shown here, to the and then via this to the image as the output image. You see that that this image here has a lot more contrast, so I can see a lot better than I could see here. Again, there's not a process of creating information, but that's a process of making it better to see. And you see that this histogram is a lot more equalized than the histogram that we obtain by only histogram equalization. Right? Okay. Then please read on page 145 to 147 from our book, the example 3.7. It's a numerical example of this process. It's very important for you to understand that. It's just 3 pages. If you have to do anything for computer vision this week, is read these 3 pages. Well, so far we've applied these histogram transformations, being it equalization or histogram matching, to the whole image. But I can also apply it to the neighborhoods, to the pixel neighborhoods. Right, so global histogram equalization and matching. So the global is that when I apply the histogram equalization to the whole image, is suitable for overall matching. But it fails to enhance details over small areas. This is obvious, right? If I'm applying the statistics over the entire image, you won't get the details of small areas, because the number of pixels in small areas is negligible. It won't affect the overall statistics. Whereas I can devise transformation function on the intensity distribution of pixel neighborhoods. Basically what we're going to do is to do histogram equalization on a moving center, on a moving neighborhood, or on a window. I'm going to move this window along the image and apply histogram equalization on every single bit of it, altering only the middle of this, on the middle of the window. So the local histogram processing procedure is the following: define a neighborhood and moves its center from pixel to pixel. At each location, obtain the histogram of the neighborhood. Apply histogram equalization or matching, depending on what you want to get from the image. Depending if you have or not a good idea of the histogram that you want to apply the transformation to the image. Change the intensity of the pixel centered in the neighborhood, move to the next, and let's see an example of it. So we have an original image, that's this one, original image. And this is the result of applying global histogram equalization. Not very good. It's you sort of see that there is some information here, but we cannot really see it. Applying global histogram equalization, we see even less. Now, if we apply a local histogram equalization, that's this, we can actually see through noise. You see, we see some stuff. We see that here there is a circle, here there is an A, here there is, well, some stuff, I don't know, something like that. So when do you apply one technique and when do you apply another technique? That all depends on the problem, and it all depends on you as computer vision scientist to decide. Right, and I can apply this to image enhancement. To image enhancement using local histogram statistics. And that's the end of this part of the lecture. On the next lecture, we're going to be talking about the most fundamental concept of the entire topic, which is convolution. You see, that's convolution that gives the name of the convolutional neural network that everybody talks about. The evil machine intelligence stuff that's going to take over the world. So you'd better learn the foundations. I'll see you in a bit.